A megatsunami is a term used for a very large wave created by a large, sudden displacement of material into a body of water. Megatsunamis have quite different features from other, more usual type of tsunamis. Most tsunamis are caused by underwater tectonic activity and therefore occur along plate boundaries and as a result of earthquake and rise or fall in the sea floor, causing water to be displaced. Ordinary tsunamis have shallow waves out at sea, and the water piles up to a wave height of up to about 10 meters as the sea floor becomes shallow near land. By contrast, megatsunamis can occur in locations where there is a very large amount of material that suddenly falls into water, or anywhere in water, or may be caused by volcanic activity, and can have extremely high initial wave heights of hundreds and possibly thousands of meters, far beyond any ordinary tsunami, as the water is splashed upwards and outwards by the impact or displacement. As a result, two heights are sometimes quoted for megatsunamis: the height of the wave itself, and the height to which it surges when it reaches land, which depending upon the locale, can be several times larger. Modern megatsunamis include the one associated with the 1883 eruption of Krakatoa, the 1958 Lituya Bay Megatsunami, and the wave resulting from the Vajont Dam landslide. Prehistoric examples include the Starego slide, and the Chicxulub, Chesapeake Bay and Elton meteor impacts. Overview: a megatsunami refers to a tsunami, a large wave due to displacement of a body of water, with an initial wave amplitude measured in several tens, hundreds, or possibly thousands of meters. Normal tsunamis generated at sea result from movement of the sea floor. They have a small wave height offshore, are very long, and generally pass unnoticed at sea, forming only a slight swell usually of the order of 30 centimeters above the normal sea surface. When they reach land, the wave height increases dramatically as the base of the wave pushes the water column above it upwards. By contrast, megatsunamis are caused by giant landslides and other impact events. This could also refer to a meteorite hitting an ocean. Underwater earthquakes or volcanic eruptions do not normally generate such large tsunamis, but landslides next to bodies of water resulting from earthquakes can, since they cause a massive amount of displacement. If the landslide or impact occurs in a limited body of water, as happened at the Vajont Dam and Lituya Bay, then the water may be unable to disperse and one or more exceedingly large waves may result. A way to visualize the difference is that an ordinary tsunami is caused by seafloor changes, somewhat like pushing up on the floor of a large tub of water to the point it overflows, and causing a surge of water to run off at the sides. In this analogy, a megatsunami would be more similar to dropping a large rock from a considerable height into the tub, at one end, causing water to splash up and out, and overflow at the other end. Two heights are sometimes quoted for megatsunamis: the height of the wave itself, and the height to which it surges when it reaches land, which depending upon the locale, can be several times larger. Recognition of the concept of megatsunami. Geologists searching for oil in Alaska in 1953 observed that in Lituya Bay, mature tree growth did not extend to the shoreline as it did in many other bays in the region. Rather, there was a band of younger trees closer to the shore. Forestry workers, glaciologists, and geographers call the boundary between these bands a trimline. Trees just above the trimline showed severe scarring on their seaward side, whilst those from below the trimline did not. The scientists hypothesized that there had been an unusually large wave or waves in the deep inlet. Because this is a recently deglaciated field with steep slopes and crossed by a major fault, one possibility was a landslide-generated tsunami. On July 9, 1958, an earthquake of magnitude 7.7 8.3 caused 90 million tons of rock and ice to drop into the deep water at the head of Lituya Bay. The block fell almost vertically and hit the water with sufficient force to create a wave that surged up the opposite side of the head of the bay to a height of 1720 feet, and was still many tens of meters high further down the bay, when it carried eyewitnesses Howard Ulrich and his son, Howard Jr. over the trees in their fishing boat. They both survived and reported that the wave carried their boat over the trees on one of the initial waves which washed them back into the bay. Analysis of mechanism. The mechanism giving rise to megatsunamis was analyzed for the Lituya Bay event in a study presented at the Tsunami Society in 1999, although this model was considerably developed and modified by a second study in 2010. Although the earthquake which caused the megatsunami was considered very energetic, and involving strong ground movements, several possible mechanisms were not likely or able to have caused the resulting megatsunami. Neither water drainage from a lake, nor landslide, nor the force of the earthquake itself led to the megatsunami, although all of these may have contributed. Instead, the megatsunami was caused by a massive and sudden impulsive impact when about 40 million cubic yards of rock several hundred meters above the bay was fractured from the side of the bay, by the earthquake, and fell practically as a monolithic unit down the almost vertical slope and into the bay. The rockfall also caused air to be dragged along due to viscosity effects, which added to the volume of displacement, and further impacted the sediment on the floor of the bay, creating a large crater. The study concluded that, the giant wave run-up of 1,720 feet at the head of the bay and the subsequent huge wave along the main body of Lituya Bay which occurred on July 9, 1958, were caused primarily by an enormous subaerial rockfall into Gilbert Inlet at the head of Lituya Bay, triggered by dynamic earthquake ground motions along the Fairweather Fault. The large mass of rock, acted as a monolith, struck with great force the sediments at bottom of Gilbert Inlet at the head of the bay. The impact created a large crater and displaced and folded recent and tertiary deposits and sedimentary layers to an unknown depth. The displaced water and the displacement and folding of the sediments broke and uplifted 1,300 feet of ice along the entire front of the Lituya Glacier at the north end of Gilbert Inlet. Also, the impact and the sediment displacement by the rockfall resulted in an air bubble and in water splashing action that reached the 1,720-foot elevation on the other side of the head of Gilbert Inlet. The same rockfall impact, in combination with the strong ground movements, the net vertical crustal uplift of about 3.5 feet, and an overall tilting seaward of the entire crustal block on which Lituya Bay was situated, generated the giant solitary gravity wave which swept the main body of the bay. This was the most likely scenario of the event, the PC model that was adopted for subsequent mathematical modeling studies with source dimensions and parameters provided as input. Subsequent mathematical modeling at the Los Alamos National Laboratory supported the proposed mechanism, as there was indeed sufficient volume of water and an adequately deep layer of sediments in the Lituya Bay Inlet to account for the giant wave run-up and a subsequent inundation. The modeling reproduced the documented physical observations of run-up. A 2010 model examined the amount of infill on the floor of the bay, which was many times larger than that of the rockfall alone, and also the energy and height of the waves, and the accounts given by eyewitnesses, concluded that there had been a dual slide involving a rockfall, which also triggered a release of 5 to 10 times its volume of sediment trapped by the adjacent Lituya Glacier, as an almost immediate and many times larger second slide, a ratio comparable with other events where this dual slide effect is known to have happened. List of megatsunamis. Prehistoric The asteroid which created the Chicxulub crater in Yucatan approximately 66 million years ago would have generated megatsunamis as high as 5 kilometers, enough to completely inundate even large islands such as Madagascar. A series of megatsunamis were generated by the bolide impact that created the Chesapeake Bay impact crater, about 35.5 million years ago. An asteroid impact in the Southeast Pacific Ocean 2.5 million years ago caused a megatsunami that was over 200 m high in southern Chile and the Antarctic Peninsula. The wave swept across much of the Pacific Ocean. The northern half of the East Molokai volcano suffered a catastrophic collapse and likely megatsunami about 1.5 million years ago and now lies as a debris field scattered northward across the ocean bottom, while what remains on the island are the highest sea cliffs in the world. A massive collapse of the western edge of the Lake Tahoe Basin, which formed McKinney Bay around 50,000 years ago, is thought to have generated a tsunami-size wave with a height approaching 330 feet. At Seaton Portage, British Columbia, Canada, a freshwater megatsunami may have occurred approximately 10,000 years ago. a huge block of the Cauche Range suddenly slid northwards into what had been a large lake spanning the area from Lillooet, British Columbia to near Birken, in the Gates Valley or Pemberton Pass to the southwest. In the North Sea, the Storegga slide caused a megatsunami approximately 8,200 years ago. It is estimated to have completely flooded the remainder of Doggerland. Approximately 8,000 years ago, a massive volcanic landslide off of Mount Etna, Sicily caused a megatsunami which devastated the eastern Mediterranean coastline on 3 continents. Historic approximately 4,000 years ago, a landslide on Ra Copyright Union Island, to the east of Madagascar, may have caused a megatsunami. 3,600 years ago, Thera volcano erupted, the force of the eruption causing megatsunamis which affected the whole Aegean Sea and the eastern Mediterranean Sea. Modern 1792, Mount Unzen, Japan. In 1792, Mount Unzen in Japan erupted, causing part of the volcano to collapse into the sea. The landslide caused a megatsunami that reached 100 meters high and killed 15,000 people in the local fishing villages. 1883, Krakatoa. The eruption of Krakatoa created pyroclastic flows which generated megatsunamis when they hit the waters of the Sunda Strait on August 27, 1883. The waves reached heights of up to 24 meters along the south coast of Sumatra and up to 42 meters along the west coast of Java. 1958, Lituya Bay, Alaska, USA. On July 9, 1958, a giant landslide at the head of Lituya Bay in Alaska, caused by an earthquake, generated a wave with an initial amplitude of up to 520 meters. This is the highest wave ever recorded, and surged over the headland opposite, stripping trees and soil down to bedrock, and surged along the fiord which forms Lituya Bay, destroying a fishing boat anchored there and killing 2 people. Howard Ulrich and his son managed to ride the wave in their boat, and both survived. 1963, Vajont Dam, Italy. On October 9, 1963, a landslide above Vajont Dam in Italy produced a 250 m surge that overtopped the dam and destroyed the villages of Longarone, Pirago, Rivolta, Villanova and Four, killing nearly 2,000 people. 1980, Spirit Lake, Washington, USA. On May 18, 1980, the upper 460 meters of Mount St. Helens collapsed, creating a massive landslide. This released the pressure on the magma trapped beneath the summit bulge which exploded as a lateral blast, which then released the overpressure on the magma chamber and resulted in a Plinian eruption. One lobe of the avalanche surged onto Spirit Lake, causing a megatsunami which pushed the lake waters in a series of surges, which reached a maximum height of 260 meters above the pre-eruption water level. Above the upper limit of the tsunami, trees lie where they were knocked down by the pyroclastic surge. Below the limit, the fallen trees and the surge deposits were removed by the megatsunami and deposited in Spirit Lake. Potential future megatsunamis. Experts interviewed by the BBC think that a massive landslide on a volcanic ocean island is the most likely future cause of a megatsunami. The size and power of a wave generated by such means could produce devastating effects, traveling across oceans and inundating up to 25 kilometers inland from the coast. British Columbia. Some geologists consider an unstable rock face at Mount Breckenridge, above the north end of the giant freshwater fiord of Harrison Lake in the Fraser Valley of southwestern British Columbia, Canada, to be unstable enough to collapse into the lake, generating a megatsunami that might destroy the town of Harrison Hot Springs. Canary Islands. Geologists Dr. Simon Day and Dr. Stephen Neal would consider that a megatsunami could be generated during a future eruption of Cumbre Vieja on the volcanic ocean island of La Palma, in the Canary Islands, Spain. In 1949, this volcano erupted at its Durazero, Hoyo Negro and Llano del Banco vents, and there was an earthquake with an epicenter near the village of Xdi. Your next day Juan Bonelli Rubio, a local geologist, visited the summit area and found that a fissure about 2.5 kilometers long had opened on the east side of the summit. As a result, the west half of the volcano had slipped about 2 meters downwards and 1 meter westwards towards the Atlantic Ocean. Cumbre Vieja is currently dormant, but will almost certainly erupt again. Day and Ward hypothesized that if such an eruption causes the western flank to fail, a megatsunami could be generated. La Palma is currently the most volcanically active island in the Canary Islands archipelago. It is likely that several eruptions would be required before failure would occur on Cumbre Vieja. However, the western half of the volcano has an approximate volume of 500 cubic kilometers and an estimated mass of 1.5 trillion metric tons. If it were to catastrophically slide into the ocean, it could generate a wave with an initial height of about 1,000 meters at the island, and a likely height of around 50 meters at the Caribbean and the eastern North American seaboard when it runs ashore 8 or more hours later. Tens of millions of lives could be lost in the cities and/or towns of St. John's, Boston, Halifax, New York, Baltimore, Washington, D.C., Miami, Havana and the rest of the eastern coasts of the United States and Canada, as well many other cities on the Atlantic coast in Europe, South America and Africa. The likelihood of this happening is a matter of vigorous debate. The last eruption on the Cumbre Vieja occurred in 1971 at the Tenagui event at the southern end of the subaerial section without any movement. The section affected by the 1949 eruption is currently stationary and does not appear to have moved since the initial rupture. Geologists and volcanologists are in sharp disagreement about whether an eruption on the Cumbre Vieja would cause a single large gravitational landslide or a series of smaller landslides, or whether a slide is likely at all. There are also questions about the dynamics. Day and Wards have admitted that their original analysis of the danger was based on several worst-case assumptions. Hawaii sharp cliffs and associated ocean debris at the Kohala volcano. Lanai and Molokai indicate that landslides from the flank of the Kilauea and Mauna Loa volcanoes in Hawaii may have triggered past megatsunamis, most recently at 120,000 BP. A future tsunami event is also possible, with the tsunami potentially reaching up to about 1 kilometer in height. According to the documentary National Geographic's Ultimate Disaster, Tsunami, if a big landslide occurred at Mauna Loa or the Helena Slump, a 30 meters tsunami would take only 30 minutes to reach Honolulu, Hawaii. There, hundreds of thousands of people could be killed as the tsunami could level Honolulu and travel 25 kilometers inland. Also, the west coast of America and the entire Pacific Rim could potentially be affected. Cape Verde Islands steep cliffs on the Cape Verde Islands have been caused by catastrophic debris avalanches. These have been common on the submerged flanks of ocean island volcanoes and more can be expected in the future. See also, 2004 Indian Ocean earthquake and tsunami, Cumbre Vieja, La Palma, list of historical tsunamis, Minoan eruption, tsunamis and lakes. References. Further reading, BBC 2 TV. 2000. Transcript Megatsunami. Wave of destruction, horizon. First screened 21.30 hours, Thursday 12 October 2000. Carrachido, J.C. The Canary Islands, an example of structural control on the growth of large oceanic island volcanoes. J. Volcanol. Jatherm Res 60, 225 a €241. Bibcode, 1994 JVGR. 6225 CDOI. 10.1016/0377-0273, 94, 90053-1. Carrachido, J.C. A simple model for the genesis of large gravitational landslide hazards in the Canary Islands. In Maguire, W. Jones. Nelberg, J.P. Volcano Instability on the Earth and Other Planets. Special Publication 110. London. Geological Society pages 125 €135. Carrachido, J.C. Growth, Structure, Instability and Collapse of Canarian Volcanoes and Comparisons with Hawaiian Volcanoes. J. Volcanol. Jatherm. Res 94, 1 €19. Bibcode, 1999 JVGR. 94, 1 CDOI, 10.1016 per second 0377-0273, 99, 00095-5. Day, S.J. Carachido, J.C. Gia, H. Gravestock, P. Recent structural evolution of the Cumbre Vieja volcano, La Palma, Canary Islands, volcanic rift zone reconfiguration as a precursor to flank instability. J. Volcanol. Jatherm. Res 94, 135 a 167. Bibcode, 1999 JVGR. 94 135 DDoI, 10.1016 per second 0377-0273, 99, 00101-8. Moore, J.G. Giant submarine landslides on the Hawaiian Ridge. U.S. Geologic Survey, D95 a 8. Professional Paper 501D. Pararas Carinis, G. Evaluation of the threat of megatsunami generation from postulated massive slope failure of island stratovolcanoes on La Palma, Canary Islands, and on the island of Hawaii, George. Science of Tsunami Hazards 20, 251 a 277. Pinter, N. Ishman, S.E. Impacts, Megatsunami, and Other Extraordinary Claims. GSA Today 18, 37 a 38 doi, 10.1130/GSATO1801GW1. Ryam, R. Crustal, S. and CD 109 Shipboard Scientific Party. 1998. Volcanoes and landslides in the Canaries. National Environment Research Council News. Summer, 16 a 17. Siebert, L. Large volcanic debris avalanches, characteristics of source areas, deposits and associated eruptions. J. Volcanol. Jatherm Res 22, 163 a 197. Bibcode, 1984 JVGR. 22 163 S-DOI, 10.1016/0377-0273, 84, 90002-7. Vorley, G. A volcanic edifice instability and tsunami generation, Monte ± a tide, Tenerife, Canary Islands. Journal of the Open University Geological Society 26, 53 a 64. Voigt, B. Jander, R. Glicken, H. Douglas, P.M. Nature and Mechanics of the Mount St. Helens Rockslide Avalanche of May 18, 190. Gar Copyright O Technique 33, 243 a 273 doi, 10.1680/Jet. 1983.33.3.243. Ward, S.N. Day, S. Cumbre Vieja volcano a potential collapse and tsunami at La Palma, Canary Islands. Geophysical Research Letters 28, 3397 a 3400. Bibcode, 2001 GeoRL 28.3397W doi, 10.1029/2001 gallons 013110. Sandham, J.G., 2010, The Wave a John Decker thriller, Cornucopia Press, 2010. A thriller in which a megatsunami is intentionally created when a terrorist detonates a nuclear bomb on La Palma in the Canary Islands. Bonelli Rubio, J.M., 1950. Contribución al estudio de la ropa en el Nombroco San Juan. Madrid, Inst. Geográfico y Catastral, 25 pp. Ortiz, J.R., Bonelli Rubio, J.M., 1951. La ropa cubed en del Nombroc. Madrid, Torres del Instituto Geográfico y Catastral, 100 p. 1 hour. Plague. 23 centimeters. External links, Megatsunami, History, Causes, Effects, Maida, Charles L. Megatsunami's description of the Lituya Bay event. World's biggest tsunami, the largest recorded tsunami with a wave 1720 feet tall in Lituya Bay, Alaska. Benfield Hazard Research Center, Science of Tsunami Hazards, a more skeptical view from the Tsunami Society. BBC Megatsunami, Wave of Destruction BBC Two programme broadcast October 12, 2000, La Palma threat overhyped, BBC News, October 29, 2004, mega-hyped tsunami story. A detailed analysis demolishing the La Palma tsunami speculation.